Welcome you in the lecture series of random processes, detection and estimation. It is third lecture of this series. In the previous lecture we have discussed about probability random variables. In this lecture we will discuss about distribution functions and mean and variance. The outline of this lecture are: we will discuss about probability mass function and its properties, cumulative distribution function and its properties, probability density function and its properties, and then conditional distribution and density function. And after this we will discuss about mean of a random variable and variance of a random variable. In the objective of this lecture, you will able to explain if PMF, CDF or PDF is given, how can you find out the probability of individual event, and what is the significance of mean and variance of a random variable. Now let us start with probability mass function. Till now we have discussed about the random variable, which is mapping from sample space to a set of real numbers, and also we have discussed about its probability distribution, means set of pair of x and its probability px. So you know the random variable is a rule or function by which a real number is given to all possible outcomes of a experiment. So we are mapping each output of the experiment to the real number. These x1 to xn are the real numbers, and the set of order pair xpx is the probability mass function PMF, and it can be denoted as pxx, means probability mass function at some real number x. It will be the probability at a random variable which is having value x, some real number x. So probability at x is equal to some real number x, and these are the properties of PMF. And the PMF lies between 0 to 1, means because this is the probability, so probability is lie between 0 to 1, and the summation of the probability or summation of the PMF, it is equal to 1. And the PMF from the definition, PMF px at x small x, it is probability when a random variable x having some real number x. Let us consider one example. An unbiased dice is thrown twice. Find the PMF of the number of sixes. So here the number of 6, if I consider the number of 6 is a random variable here, so x is the random variable denoting the number of 6 occurs, and I am throwing a dice 2 times. This means I can have the 6 in 0, 1 or 2 times. 0 means I am getting 6, I'm not getting 6 none of the 2 thrones, and 1 means I am getting 1 6 in 2 thrones, and 2 means I am getting 2 6 in all 2 thrones. So now for the PMF x px is equal to 0. This means probability when a random variable x having the value, this real value 0. So it will be, this is the probability of not getting 6 in both the thrones. So means in the first throne, the probability of getting 6, it is 1 by 6, and not getting 6, it will be 1 minus 1 by 6. So 1 minus 1 by 6 in the first throne, and 1 minus 1 by 6 in the second throne. So the probability of not getting 6 in both the thrones is 25 by 36. And px 1 means the PMF at x is equal to 1, or you can say the probability when random variable having real number x1. And the meaning of this is that the probability of getting 1 6 in 2 thrones. So means you can have the 6 in the first throne, or you can have the 6 in second throne. So the probability of getting 1 6 in first throne, it is 1 by 6, and not getting in second throne, it is 1 minus 1 by 6. Or not getting 6 in first round, 1 minus 1 by 6, and getting 6 in second round, it is 1 by 6. So the probability of getting 1 6, it is 10 by 36. And similarly, the px2 means probability of getting 6 in both the thrones. So in first round, probability of getting 6, it is 1 by 6, and probability of getting in the second throne, it is 1 by 6. So the probability of getting the 6 in both the thrones, it is 1 by 36. So if you want to sketch the plot of this PMF, so the random variable having value 0, 1 and 2, and the corresponding probability corresponding to this random variable 0, 1, 2, that is 25 by 36, 10 by 36 and 1 by 36. So I can plot this. It is the random variable x having value 0, 1 and 2. So at x is equal to 0, the probability is 25 by 36, and at x is equal to 1, the probability is 10 by 36, and at x is equal to 2, the probability is 1 by 36. So from this curve, you can find the probability of getting 1 6 in two thrones, and you can see it is 10 by 36. So from this graph, you can show that the probability of getting 1 6, it is 10 by 36, and probability of getting 2 6 in two thrones, it is 1 by 36. Now, cumulative distribution function. Summing the probabilities of a discrete random variable is the cumulative distribution function. There are many problems where we may wish to compute the probability that observe the value of random variable x will less than or equal to some real number. Means you want to find out the probability of x that having less than equal to some real number x. Then when probability when x less than equal to some real number, and means we are getting the sum of the probabilities less than equal to 1, this is known as the CDF, and where x lies between minus infinity to infinity. And when we have done the PMF, we can add up all the PMF, and we can find out the CDF. So CDF, in the case of when PMF is given, the summation of PMF will be the CDF, cumulative distribution function. Now the properties of CDF. So there are different properties of CDF. The first property is the CDF lies between 0 to 1, because the CDF is the summation of the probabilities, so it will lies between 0 to 1. This first property shows that because fx is the probability, right? And fx x1 less than equal to fx x2 if x1 less than x2, and this property shows that fxx is non-decreasing function. And the third property, limit x tends to infinity, fxx, it will be equal to fx at infinity, value of x is infinity here, and it will be equal to 1. And limit x tends to minus infinity, fx means fx minus infinity, and it is equal to 0. And these properties follow axiom 2. This means PS is equal to 1. So means probability of all the sample points, means because this includes all the sample points, and the probability of sample points of all sample points, it is 1. And the fourth property indicates the property second, and it is probability of null set is 0, means because this indicate there will be no sets, and the probability of null set is 0. And the fifth property, limit x tends to a plus fxx, this means fxa plus, and this is fxa, and this property indicates that fx is continuous on right. Now consider the previous example, 26 example, where we have considered the unbiased dice is thrown twice, and random variable x was the number of 6. So we have thrown the dice 2 times. So in one in one zone, the number of outcomes will be 6, and in the second number of outcomes will be 6. So there will be total 36 outcomes in this case. So here fx naught means probability x less than equal to 0, and here the meaning of this is that a probability of not getting 6, and it is 25 by 36, and fx1, this means probability x less than equal to 1, means probability is 35 by 36, and CDF at x is equal to 2, this means probability x random variable x less than equal to 2, means probability at x is equal to 0 plus probability at x is equal to 1 plus probability at x is equal to 2, and probability at x is equal to 0 is 25 by 36, and probability at x is equal to 1 is 10 by 36, and probability at x is equal to 2 is 1 by 36, so it is 36 by 36 1. So the CDF at x is equal to 2, it is 1. So here we can sketch the CDF. This is the CDF. Here the value of x is 0 1 2, and the value of CDF fxx at x is equal to 0, it is 25, at x is equal to 1, it is 25 plus 10 by 36, it is 35 by 36, as we have measured. X is equal to 2, it is 1. And these are the jumps at, this is the jump at point 1, and this is jump at x is equal to 2, and these jumps indicate the PMF, or you can say that the probability of getting 1/6 in 2 zones, it is 10 by 36. These jumps indicate the probability at this random variable, and the CDF at the random variable x, it will indicate in this side. This is the CDF at random variable x, 35 by 36, and the probability at random variable x indicates the jump, or you can say this is the PMF, 10 by 36. And most of the information about random experiment are described by the random variable, which is determined by the behavior of the CDF. Now let us consider one example. Consider the experiment of tossing a fair coin 3 times, and let a random variable x is the number of heads obtained there. So sketch the CDF of the random variable x here. So I'm tossing a coin 3 times. So in the first time, if I'm tossing a coin, there will be 2 possible outcomes, and I'm tossing 3 times. So the total number of outcomes, it will be 8. So the total number of outcomes in the sample is 8 here, and the random variable x is the number of heads, and in tossing a coin 3 times, so the number of heads, it will be maybe 0 1 2 or 3. So the value of random variable x may be 0 1 2 or 3. This means 0 means I'm not getting head in 3 tosses. I'm getting 1 time head in 3 tosses, I'm getting 2 times head in 3 tosses, and I'm getting head 3 times in 3 tosses. So the event x less than equal to x, this means I'm getting no head. So this means the event will be tail tail tail, and if I'm when x is equal to 1, so x less than equal to 1, the meaning is here means the event which is having the head in 1 time or 0 time. So TTT, TTH, THT, TTH. So there are total possible ways are 1, 2, 3 and 4 different ways, and the total number of ways are 8 here, total number of sample points. So the fxx means fx at x is equal to 0, means you can say the probability when x less than equal to 0. You can see here this is the one favorable outcome here only. So favorable outcome upon total number of outcomes, so 1 by 8 here. And for this case, when x is equal to 1, the favorable outcomes are here 4 and total number of outcomes are 8. So probability x less than equal to 1, so it will be 4 by 8. And when x is equal to 2 means I am getting head no times, 1 time and up to 2 times. So summation of means I am including all the events which are having less than 2 heads. So less than or equal to 2 heads. So h h t h t h t h h and t t t t t h t h t and h t t h. So there are 7 possibilities. So the CDF at x is equal to 2, it is 7 by 8. Similarly, the CDF at x is equal to 3, it is 8 by 8, 1. So I can sketch this CDF here, random variable x having value 0, 1, 2, 3, and x is equal to 0. You are having the CDF at 1 by 8. So 1 by 8, and when x is equal to 1, the CDF is 4 by 8. So this is 4 by 8, and when x is equal to 2, it is 7 by 8, and when x is equal to 3, it is 1. 8 by 8, it is 1. And these jumps indicate the probability at these points, means probability of getting 1 head in 3 tosses. So it is the jump at this point, or PMF at this point, and it is 3 by 8. So the 3 by 8 is the probability of getting 1 head in 3 tosses, and probability of getting 2 head in 3 tosses, it is 4 by 8, this jump. And if I want to find out the CDF at point x is equal to 1, so CDF is 4 by 8 at x is equal to 1, and the CDF at x is equal to 2, it is 7 by 8. So here we can see that if x is a random variable with CDF fxx, fxx changes value only on jumps, as in the previous case you have seen. This only change value at these jumps 1, 2, 3, and so now we can say that fxx is the staircase function. And then if you can say that xi greater than xi minus 1, so at this point this jumps indicate the PMF, or you can say if this is CDF, and this is the value of CDF at xi, and this is the value of CDF at xi minus 1. So if I subtract this CDF at x is equal to I minus this CDF at x is equal to I minus 1, I will get this jump PMF. So the PMF at x is equal to xi means probability at x is equal to xi. This will be the subtraction of the CDF at x is equal to xi minus CDF at x is equal to xi minus 1, and this is the PMF here. And this shows that how much jumps at x is equal to xi from the previous value, or the probability at a particular point, and this is the PMF. And the plot of x and px is known as the PMF curve or bar chart. Some properties of CDF are probability when x lies between a to b, and here b is included, means x less than equal to b but x greater than a, and it will be the fxb minus fxa, means CDF at x is equal to b minus CDF at x is equal to a. And the probability when x greater than a, this means you can say that 1 minus probability at x less than equal to a, the meaning of this probability x greater than a. So you can say this is 1 minus, and this is the CDF at x is equal to a. So 1 minus CDF at x is equal to a. And probability when x less than b, this means the CDF at x minus b. And the probability when x lies between a and b, this means I'm here at this time I'm not including the b value of random variable x. So now in this case it will be equal to CDF at x is equal to b minus CDF at x is equal to a, and minus probability at x is equal to b. And when the probability of x less than equal to greater than equal to a and less than b, here I am including a, not including b. So it will be equal to the CDF at x is equal to b minus CDF at x is equal to a plus PMF at x is equal to a minus PMF at x is equal to b. Now consider the experiment involving two dice. The sum of the dots appear on the two dice is the random variable x. Now plot the CDF and PMF. So I'm having two dice, rolling two dice. So in the first dice the outcomes are 6, and in the second dice total outcomes are 6. So there are total 36 outcomes will be there, and so the outcomes 36, and the random variable x is the sum on the dots of the two dice. So it may be from 2 to 12 sum of the dots. And for sketching the CDF or PDF, let us take when x random variable x having the value 0. The meaning of this random variable x having 0 means there is null set, no event will come, means you cannot have any type of event that having the sum on the dots is 0. So this is the null set, and 1, and also it will be the null set. There is no possibility to having the sum on the two dice is 1. And when x is equal to 2, this means I am getting the sum on the dots is 2. This means getting the 1 in the first dice and getting 1 in the second dice. So the sum of these two will be 2. So the favorable outcome is this is 1 outcome. And for the case of x is equal to 3, the favorable outcome will be 1 2 and 2 1. And for x is equal to 4, the favorable outcome may be 1 3, or it may be 2 2, or it may be 3 1. So there are 3 possibilities. So the PMF at x is equal to 0. This means probability at when x is equal to 0, or probability of phi null set, it is 0, and probability of null set, it is 0. And the probability of when random variable x having value having the sum on the dots is 2. This means random variable having the value 2. This is only one favorable event here. So the probability or PMF at x is equal to, it is 1 by 36 favorable, total number of favorable events divided by the total number of events. So 1 by 36. And when x is equal to 3, the probability or PMF at x is equal to 3, it is 2 by 36. 2 favorable events are here, and this is 3 favorable events. So the PMF at x is equal to 4, it is 3 by 36. Now the CDF at x is equal to 0, null set. So probability of null set is 0, probability of null set is 0. And fx2, this means the probability when x less than equal to 2. This means you can say that probability when x is equal to 0 plus probability x is equal to 1 plus probability when x is equal to 2. So here you can see 0 plus 1 by 36. So summation of all PMF at x is equal to 2. So it is 1 by 36. And the CDF at x is equal to 3. It is summation of all previous up to 3 at x is equal to 3. So it is 1 by 36, and it is plus 2 by 36 at point 3. So 1 by 36 plus 2 by 36, it is 3 by 36. This is the CDF at x is equal to 3. And CDF at x is equal to 4. It will be 3 by 36 plus 3 by 36. So it is 6 by 36. Similarly, when x is equal to 5, the favorable event or the outcome may be 1 4, 2 3, 3 2, 4 1. and the PMF at x is equal to 5. It is the favorable are 3 here. Outcomes of 4 outcomes are favorable here, so 4 by 36, and the CDF at x is equal to 5. It is in the previous case the summation was 3 by 36 and plus 4 by 36, so it is 10 by 36. CDF at x is equal to 5, and for x is equal to 6 the favorable outcomes are 1 5 or 2 4 or 3 3 or 4 2 or 4 1. So the PMF at x is equal to 6, it is 5 by 36, and the CDF at x is equal to 6, it will be 10 by 36 plus 5 by 36, it is 15 by 36. So for the case of when x is equal to 7, the PMF it is 6 by 36, and the CDF at x is equal to 7, it is 21 by 36, and for x is equal to 1, x is equal to 8, and this means the sum on the two dice is 8. So the PMF at x is equal to 8, it is 5 by 36, and the CDF it is 26 by 36. And for the case of x is equal to 9, the favorable outcomes are 3 6 4 5 5 4 6 3. So the PMF at x is equal to 9, it is 4 by 36, and CDF it is 30 by 36. And when x is equal to 10, the PMF will be 3 by 36, and the CDF is 33 by 36. And for x is equal to 11, so the PMF it will be 2 by 36, and the CDF it is 35 by 36. And for the 12, only one case here, one outcome may be 6 or 6. So the probability it will be 1 by 36, and the CDF is 1. So now I can sketch the PDF and CDF. I am having all the values at different random variables. So the random variables, the random variables are may have the value 0 1 2 3 4 5 6 7 8 up to 12, and I have scaled here 1 by 36, 2 by 36, 3 by 36, and so on. So you can see that at x is equal to 0, it is 0, at 1 it is equal to 0, and when x is equal to 2, the CDF was 1 by 36, and for x is equal to 3, it is 3 by 36, then 6 by 36, 10 by 36, then 15 by 36, 21 by 36, 26 by 36, 30 by 36, 33 by 36, 35 by 36, and 36 by 36. So this is the value of the CDF, and so you can sketch this is the sketch of the CDF, and this is the staircase CDF. And here you can see the probability when the sum on the dots is 4. So it indicates the probability the probability indicates the jump. So the probability if you are getting the sum on the dots is 4, the probability of getting the sum on the dots is 4. This is 3 by 36, this jump, and if this was 3 by 36 and it is 6 by 36, so this is 3 by 36. Now the PMF, at different value at x is equal to 2, it is 1 by 36, at x is equal to 3, it is 2 by 36, when at x is equal to 4, it is 3 by 36, and when x is equal to 5, it is 4 by 36, at x is equal to 6, it is 5 by 36, when x is equal to 7, it is 6 by 36, and again when x is equal to 8, it is 5 by 36, 4 by 36, 3 by 36, 2 by 36, and 1 by 36. So it is the PMF curve or bar chart, and it describes the jump at x from the previous value x minus 1 in the case of in the previous case CDF. So if I want to find out the probability of getting sum on the two dots is 4, and you can see it is 3 by 36. 3 by 36 it is. So as you have seen in the previous case, it was the jump at x is equal to 4. Now I can plot the rectangular curve, you can say histogram. So you know this is the PMF curve, and if I am going to sketch this rectangular, so it will be the histogram curve. So till now we have discussed about discrete random variable, which is a mapping of each sample point to the real number. Now we will take a look of a continuous random variable and probability density function. A continuous random variable is a mapping from the sample space S, which is continuous, to a numerical space Sx, which is a set of real lines. Sx is this is the set of real lines, and this is the set of continuous sample space. And for example, consider the experiment of gun shooting, where target can be anywhere at the circular board, as you can in this figure. The outcome of the shooting experiment is the point S1. Consider this is the point S1 of the outcome of the shooting, and this is the circle of radius 1, and the distance from the center is measured, and the value is assigned to the random variable or S1. So this distance is measured from the center, and we are going to assign the value in the real line as x, and it is x1. So x1 belongs to between 0 to 1. So this x1 can be anywhere between 0 to 1, and this x1 is the continuous random variable. Also, if x is a random variable with CDF fxx, if fxx is continuous and also have the derivative dfxx by dx, then the random variable is known as the continuous random variable. In most applications, the random variable is either discrete or continuous, but if the CDF fxx of a random variable having the features of both discrete and continuous, then a random variable is known as the mixed random variable. Now, after defining the continuous random variable, we will discuss about the probability density function PDF. The probability density function of a continuous random variable can be represented by the function fxx, and which is usually termed as probability density function, or simply the density function of random variable x. The derivative of the cumulative distribution function fxx is the probability density function of random variable x. So fxx is the d by dx of CDF, and if x is discrete type random variable, then fxx it will be the summation pi del x minus xi, and this del x minus xi is the impulse at that point, whose magnitude will be the probability at the point, as you can see in the previous example number 29. And a probability density function is constructed so that the area under the curve bounded by the x-axis is equal to 1 when computed over the range of random variable x, for which the PDF fxx is defined. And there are some properties of this PDF. The first property is fxx greater than equal to 0, means because this is the probability, so this indicates the non-negativity. This means the PDF is the positive, and the integration minus infinity to infinity, the PDF dx is equal to 1. This indicates the area under the curve of the PDF is equal to 1, and the probability when x lies between a and b, and if x is also equal to b. So you know, from the CDF property, it is fxb minus fxa, means CDF at x is equal to b minus CDF at x is equal to a. And in the PDF form, I can write it as integration from a to b, and the PDF fxx into dx. And the CDF fxx of a continuous random variable x, it will be if we have given the PDF. So CDF, it will be, the probability when x less than equal to x. And from the property, from the definition of the PDF, you can write it as integration minus infinity to x, and fx xi d xi means the PDF of the random variable x. Now let us consider one example. The PDF of a continuous random variable x is defined as fxx. When x lies between 0 to 1, it is 1 by 3, and when x between 1 to 2, it is 2 by 3, else it is 0. And for this sketch PDF, so you can sketch the PDF you have given. When x lies between 0 to 1, the value of the PDF, it is 1 by 3. So here it is 1 by 3 from 0 to 1. And when x between 1 to 2, the value is 2 by 3. So it is 2 by 3 at this point, else it is 0. So here and here it is 0. So you can see that there is jump at 1. Here this is jump, and the jump is 1 by 3. Now find the corresponding CDF and sketch it. So the CDF fxx in terms of PDF, it is from integration from minus infinity to x fx d xi. So you can find out when x less than 0, it is 0. When x between 0 to 1, so you have to integrate from 0 to x. So the integration from 0 to x, and between 0 to 1, the PDF is 1 by 3. So this is integration from 0 to x, 1 by 3 dx or dxi. So it is x by 3. And when x is between 1 to 2, so the CDF is the CDF is the summation. So it is from 0 to 1 and 1 to x. So the integration from 0 to 1 of the PDF 1 by 3 d xi, and 1 to x 2 by 3 d xi, and it will be equal to 2x by 3 minus 1 by 3. And when x greater than 2, this means you have to sum up of these from 0 to 1 and 1 to 2. So 0 to 1, the PDF 1 by 3 d xi, 1 to 3 2 by 3 d xi. So it is 1. So now you can sketch the CDF here. From 0 to 1, it is x by 3. So it is x by 3, and from 1 to 2, it is 2x minus 3, 2x by 3 minus 1 by 3. So it is 2x by 3 minus 1 by 3. And from 2 to 3 or greater than 2, it is 1. So you can sketch like this. It is the CDF. Now consider another example. Let x be a continuous random variable with PDF kx when x is between 0 to 1, else it is 0. Find the value of this constant k. So the area under the PDF is 1. So integration from minus infinity to infinity fx dx is 1. So fxx is kx here. So and the value of x is from 0 to 1. So integrate from 0 to 1 kx dx is 1, and from this you can find out the value of k is 2. So you can define now the PDF is 2x when x is between 0 to 1, else it is 0. You can sketch this PDF like this. When it is between 0 to 1, the value is 2x. So at 0 is equal to 0, and at x is equal to 1, it is 2. So you can sketch this. This is 2, else it is 0. In this case it is 0. And the second part is find and sketch the corresponding CDF. The CDF is integration from minus infinity to x of PDF. So you can find out when x less than 0, it is 0, and when x between 0 to 1, so integration from 0 to x of the PDF 2 xi d xi, it is x square. And when x greater than 1 means from 0 to 1, integration of xi, it is 2 xi, and it will be equal to 1. So you can sketch here, you can see from 0 to 1 it is x square, and from 1 to 2 greater than 1 it is 1. Now the third part is find a probability when x between 1 by 4 and 2. So you can find out from the property, it is the PDF, the CDF at x is equal to 2 minus CDF at x is equal to 1 by 4. Or you can say it is f at the CDF at x is equal to 2, it is 1, and the CDF at x is equal to 1 by 4. So it is 1 by 4 is to the square, so it is 15 by 16. Now conditional distribution. We know that the conditional probability of a event A, given that the event already happened, so probability A by B, you know, this is the joint probability P A intersection B divided by probability of B. Now we extend this conditional probability concept. Let A is the event, x less than equal to x. This is the event, and this event having the sample points xi, and this is such that the random variable x xi less than equal to some real number x. So the probability x less than equal to x given event B, so it will be, you can write it as fx x by B, means the CDF at the value of random variable x when event B already happened. Or you can write it as the probability when x less than equal to x and intersection B, means the joint probability of this event and event B divided by the probability of D. And this is known as conditional distribution. Now the properties of conditional distribution: fx minus infinity and B already happened, it is 0. Fx infinity divided by when B is given, it is 1, and the conditional PDF x by D, it is lie between 0 to 1, and the conditional PDF at x is equal to x1 given B less than equal to the conditional PDF at x is equal to 2 given B if x1 less than x2, and the probability when x random variable x is between x1 and x2 when the event B already happened. So it is the conditional CDF when x is equal to 2, and conditional CDF at x is equal to x1, and the sixth property is the CDF at x is equal to x plus, and when B is already happened, so this is fxxd. So you can say this is continuous on right. So here these characteristics have the same general meanings as in the previous CDF case. Now the conditional density. Similarly to the density function, we can define the conditional density function of random variable x as the derivative of the conditional CDF. So fxx, it will be d by dx of fx by v. So it is conditional PDF. And the properties of the conditional PDF: fx, the conditional PDF of x given b, is greater than or equal to 0 non-negative, and the area under the conditional probability it is 1, and CDF conditional CDF fx x given b, and it can be defined as integration minus infinity to infinity the conditional PDF with given the event b, and the probability when x lies between x1 to x2 given probability b, the event p. So it will be the integration x1 to x2 and the conditional PDF. The important concept in the probability and statistics theory is the mathematical expectation, or the expected value, or the mean, or the statistical average of the random variable. Now we will discuss first the mean value. The mean or the expected value of a discrete random variable x is equal to the sum of the value of random variables xi and weighted by the probability of that particular value, and this is the probability of the xi. So the mean value or expected value of random variable x, it is denoted by ex, expected value of x, or you can denote it as mu x or mx or x bar, and it is summation I xi t xi. And similarly, the mean value for a continuous random variable, it will be the integration from minus infinity to infinity x and PDF of the random variable x. So here it is weighted by the PDF of the random variable, and in the discrete case it is weighted by the PMF, or the probability of that particular value. So here consider one example. Two coins were tossed and let the number of heads of the experiment is the random variable. Then find the mean value of the number of heads. So here the sample space when I'm tossing two coins, so it will be head head, head tail, tail head, and tail tail. So and the total number of sample points here are 4. And we have the random variable is the number of head. So the value of the random variable or number of head is 0, 1, 2, and the probability of x is equal to 0 means probability of getting no head means probability of getting tt. It is 1 by 4, and probability when x is equal to 1, it means the probability of th or the probability of ht is 1 by 2, and probability at x is equal to 2, it is 1 by 4. So from here you can find out the expected value of the random variable x, or the number of heads, and from the definition it is summation I xi pxi. So when x is equal to 0, the probability is 1 by 4, and when x is equal to 1, probability is 1 by 2. When x is equal to 2, the probability at x is equal to 2 is 1 by 4. So we can get, and the expected value here is 1. So this means that the person who toss two coins over and over again, on the average he get 1 head per toss. Now the moment of the random variable. Let us consider a new random variable gx, which is function of random variable x. Gx is equal to x square. You may also consider like 3x minus 1, and so any function of random variable x. So in the previous case you have seen that I'm tossing a coin 2 times. So these are the possible outcomes h, ht, th, and tt. And the random variable is a rule by which or a function by which can assign a real number to all possible outcomes. So here the random variable x is the number of heads. So by this rule we can assign the value of these outcomes of the experiment. H is defined by the outcome h is assigned a value 2, and we have assigned ht, th is the value 1, real number 1, and for tt we are assigning value 0. And now some other function that is a function of random variable x is x star. So I'm mapping 2 into the 4, 1 in 1, and 0 is 0. So here if I am having x random variable x having value 0, 1, 2, and now gx will be 0, 1, and 4, the value of gx, and the probability of gx. So get the probability of this 4 means the probability of this random variable x is equal to 2, and probability of this gx 1 means the probability of this x random variable x. So here the probability at 0, probability at 1, and probability at 2. So from here you can see the expected value of a random variable gx. It will be in discrete form summation gxi pxi. Here pxi is not changing here because the probability at gx is equal to 2 means the probability at x is equal to 2. So and for the continuous case the expected value of gx, it will be the gx into the PDF of random variable x, fxx dx. So now we can define the moment of the random variable. You know, from the previous slide, expected value of gx, it is gx fxx dx, gx into PDF and integration from minus infinity to infinity. So if here gx is equal to x is to the power n, and the expected value of x is to the power n, it is integration from minus infinity to infinity x is to the power n, and the PDF of random variable x dx for continuous case. And for discrete case, it is summation I x I is to the power n p x I, and for the discrete case is the PMF. And the expected value of gx is equal to x is to the power n is the nth moment of the random variable. So here you can see if n is equal to 1, we can find out the mean of the random variable. So the mean of the random variable when x is equal to 1, nth moment of the random variable or first moment of the random variable is the mean value, and this is the integration from minus infinity to infinity x and fxx dx. And the second moment of the random variable, similarly you can find out ex square, it is integration from minus infinity to infinity x square fx x dx. And this second moment is known as the mean square value. Now, variance of a random variable. The mean or the expected value of the random variable x is of special importance because it describes where the probability distribution is centered. So by the mean value means if you are having this type of PDF and this is the mean value, so you can say your PDF is centered at the mean value. However, the mean does not give the description about the shape of the distribution. For this, we need to characterize the variability in the distribution because you cannot find out the shape, what is the shape, like this or like this. So what will be the shape? So variance will give you this type of shape description. The variance of a variance of a random variable x is a measure of the variable's dispersion from the mean value. And to define the variance, let x is equal to x minus mu whole square, where mu is the mean of the random variable x. Now the expected value of this gx means expected value of the whole square of x minus mu, and this is the variance of the random variable. This means the expected value of x minus mu whole square, it will be the variance. So variance will be expected value of this means integration from minus infinity to infinity whole square of x minus mu into PDF, and this is denoted as sigma square variance. And another important parameter is the central moment about the mean. It is defined as the moment of the difference between the random variable x and its mean value. So the nth moment means x minus mu is to the power n. The nth moment means expected value of x minus mu is to the power n. This is the nth moment of the nth central moment of the random variable x. So nth central moment is the integration from minus infinity to infinity x minus mu is to the power n and the PDF. So from here you can see this is the second central moment of the random variable x. If I am going to put the value n is equal to 2, it will be the variance. So second central moment of the random variable is the variance. There is one theorem related to the variance. Variance means the second central moment means expected value of the x minus mu whole square. It will be integration from minus infinity to infinity x minus mu whole square and the PDF, and it will be equal to the mean square value minus the whole square of the expected value of x. This means the variance is the difference between the mean square value of the random variable x and the square of the mean value of the random variable x. Now let us consider one example. Let the random variable is the number of defective parts for a machine when three parts are sampled from a production line and tested. The following is the probability distribution. The random variable x is having value 0, 1, 2, 3, and the probability distribution is 0.5, 0.38, 0.10, and 0.01. So find the mean and variance. You know the mean is summation x and weighted by the probability of that particular value of x. So here x is 0 and the probability of this x0 is 0.5. So 0 into 0.5 plus 1 into 0.38 plus 2 into 0.10. So you can find out the expected value of the random variable x is 0.61. And to find the variance, you know the variance is the mean square value minus the whole square of the mean value. So the mean square value you can find out, it is summation x square and px, and from this you can find out the mean square value is 0.87. And so from equation first you can find out the variance is 0.87 minus 0.61 whole square of the mean. So the value of the variance is 0.497. There are some important distribution functions that are frequently used. We will discuss some discrete and continuous distribution function in the next lecture. The discrete distribution functions are Bernoulli distribution, binomial distribution, and Poisson distribution. And these Bernoulli and binomial distributions are used for testing the items, or that is defective or non-defective, and the Poisson distribution is used when the number of outcomes occurring in one time interval or a specified region, that is the number of call drop during the busy hours. And the continuous distribution functions are, these are uniform distribution function, exponential distribution function, normal or Gaussian distribution function. There are many more distribution functions, but now here we will discuss only these three. So a uniform distribution is used where we have no prior knowledge of the actual PDF and all the continuous variables in some range seems equally likely. And the exponential distribution is useful in describing the raindrop size when a large number of rainstorm measurements are made. It is also used to describe the fluctuation in the signal strength received by the radar from the certain type of aircraft. And the normal distribution describes many phenomena that occur in the nature, industry, research. Error in scientific measurements are extremely well approximated by the Gaussian distribution. For the time being, this was the lecture 3rd of the lecture series of random processes detection and estimation. In the next lecture, we will discuss in detail about these probability density function, discrete type and continuous type. Till then, thanks for listening this lecture. Thank you.